Carnot thermodynamics principles. So thermo comes from heat. We're going to be talking about a lot of heat. So a Carnot engine is an engine where the processes are quasi-static. It's a perfect engine. There's no friction. There's no any kind of environmental loss. It's a perfect engine. So that engine where the processes are quasi-static, perfect, no losses, nothing. So let's imagine we have gas here at a high temperature. Let's call it TH. It's connected to reservoir TH, which replaces any heat loss it has. So then there is QH going into the system. Now we know that Q here, we're going to have QH over here. So we do have Q in this scenario. Since T is always TH, delta T is always 0. R is a constant and it's a closed system, so it's also 0. So the delta here is 0. So we understand that the delta here is going to be 0. Now, in this side also, in this function also, the delta here is 0. If no matter how many gases there is, this number changes, this doesn't change, so the delta is going to be 0. So the internal energy is 0. So then we know very easily that Q is equal to W. You might tell me, well, we have Q, where is W? W is a change in volume. You might ask me, well, it's delta 0, delta PV is equal 0. Well, it's being compensated by P. So if you look over here, P is equals 1 over V and V is equals 1 over P in this scenario. So if you look at this chart, the first step, first process, 1 to 2, is an inversely proportional function. Obviously, I didn't draw it properly in short, but you can get the image. So it goes like this. It increases, but we don't reach full volume. Oh, well, that's because before we reach the end, we remove the reservoir. No reservoir anymore. We put in work into the system to pull it down. Well, since there is no reservoir, this is not equals to 0 because we do have a change in T, because T can change. When we pull it down all the way, well, you put in work. By putting in work and increasing this, it's W, you have W. So minus W equals minus U, obviously. So now we have a decrease in U. Delta, this is going to be negative. This is also going to be negative. So that means we have a decrease in temperature. That decreased temperature, let's call it TL. Now we have the piston all the way down. It's at temperature TL. Okay, we are over here. Now, by going this way, how do we do it? We put a reservoir of TL also, and we push it by having the reservoir over there. Any loss of temperature is going to be, any heat is going to be sent here. So now we have heat. We will probably have work again because the temperature is constant. So we are going to have work. This time it's negative Q, so it's going to be plus work. Negative work, which here is going to be plus because it's two negatives. So that negative work means we have a lower volume. Again, we go PV, V equals 1 over V, So it's a inversely proportional function again, where it goes up right before the end. Same exact thing before we get there. We remove the reservoir. Now when we remove the reservoir, we're pushing it up. T can change. We are putting negative work because it's a smaller distance now, and we're making the distance smaller. Negative work, negative and negative is going to be positive. Positive U, and then T is going to go up. Now we reach TH. So if you ask me first, why did we get to TH? Is it because of the reservoir? No, we were at TH without the reservoir. So now that we understand Carnot's engine, we are going to look at its functions. So the first function is the efficiency of a heat engine is equals to 1 minus QL over QH. This is for reversible and irreversible engines, perfect and imperfect engines. But this function, 1 minus TL over TH, is only for perfect engines. This is because perfect engines have TL over TH is equals to QL over QH due to the lack of loss. So Carnot's first principle says that a reversible quasi-static perfect engine is always more efficient than an irreversible engine. So if someone tells you about a heat engine that is more productive than 1 minus TL over TH in terms of efficiency, they're lying. So this is the first principle. Second principle is, if you have two perfect engines connected to two reservoirs of the same temperatures, it's always going to be the same efficiency. No matter how big the engine is, how small the engine is, a Carnot perfect reversible quasi-static engine is always going to have the same efficiency given the same TH and TL. That's it. Thank you.